Okay, so I'm going to talk about the finite element method. Okay, I'm going to send this word to you. But if you can take notes also, that's okay. Okay. First, the finite element method is an interpolation method. Okay, so it means that you can interpolate, for example, let's see 2D structures. Okay, let's see a 2D domain. For example, imagine that you have a territory, okay, like Portugal, okay, and you know that in some places, for example, here, you know the temperature. You know this temperature, here the temperature here, etc. So if you know the temperature of several points in the territory, maybe you can fit that temperature, that field, that is a field of temperatures, maybe you can fit it to a surface, okay? And then you can interpolate the surface, you can interpolate to any other point. For example, imagine that you want to know the weather in Lisbon, and you just interpolate and know the value here of the function. That is interpolation. It's not the real temperature there, because you only know the temperature of this point, that point, and that point. So you are interpolating, you see, you are interpolating the temperature on that point. So finite element method allows you to do that. You're going to see in the text that you are going to read that finite element method, using the stiffness matrix that I'm going to show you what it is. Stiffness matrix exponential -1 multiplied by the force applied to your structure allows you to obtain the displacement field. Okay, so finite element method allows you to obtain displacement fields. Okay, so let's assume that you have a solid domain. Okay. And with this domain, okay, you have inserted here some forces. I'm just writing triangles, okay? This is your domain. And you put here some boundary conditions, say this node does not move, this also is fixed, and I'm putting here a force, okay? It happens that when you do this, your domain, complete domain, it's going to deform, okay? It takes this shape and it moves, for example, to, let me put here, okay, and all the points, they go to this position, okay? So this point here have moved to here, okay? Every triangle inside has changed from its original position to another position, for example, this one. If you put the dots, for example, this point on top of that one, well, you don't need to do that, but you understand that this one has a displacement and this one has another displacement, you see, on y and x, and this also has a displacement is smaller and on y is larger, and this one has a displacement on y and on x. This leads me to the degree of freedom. Degree of freedom. This is an important concept in finite element method. It has its own acronym, it's DOF, okay? And in 2D, a point has 2 degrees of freedom. It can move freely on U and V, being this the y-axis and this the x-axis. So every time you do something in 2D, the x is linked to u and y is linked to v, okay? And a particle can move only on x and y. Every other position is a decomposition. For example, if it starts here, okay, it will end here. And if you see, this position is a composition of v and u, okay? So these are the 2 degrees of freedom that we have in finite element method. So let's imagine the following. Let's imagine that we have, for example, let's choose here a triangle, okay? And let's imagine that in that triangle, what is happening? let's imagine that in this triangle, okay, this is a triangle, and these are the axes, x and y. And let's imagine that you have here node I, node j, and node k, okay? And we are interested to know the displacement of this point here, this inner point. It does not matter if it is the center or not of the element, okay? It does not matter that. It is a point, any point. It can be closer to y or j or k, or it can be in the middle, never mind. Let's call this point our x, capital I, okay? Capital I, not small I, capital I, okay? And this will be our node x, y, x, j, x, k, okay? These are our three nodes composing the triangular element, and this is the node that we want. Well, what do we know? We know that every node, okay, of the triangle has its own displacement. You see it here, okay? So we can maybe, yeah, we can put this in a 3D view, where here we can draw the U. Okay, these are the points, the I, the J, and the K. And now I'm plotting here the displacement. For example, positive, a little bit, negative, just a small one, and a larger one on X, positive. So our surface is something like this. This is the surface of the displacements. You're going to understand this better when I finish. Okay, this surface here. Okay, this is the surface. Can you see it?
Yes.
Well, this surface here, if you know the expression of this surface, you could easily go to this central point and obtain the interpolated displacement, capital I. You understand that? You can do the same, if you want, for the V. So here up the X, the Y, okay, X, Y, and now the V for displacements on V. So you have here the same triangle, it's the same, exactly the same, but now you see V is down, is negative in this point. In this one is also negative, but it's a larger one, and this one is a smaller one, like this. So here our surface is like this, okay? That is similar to the other one. And you can have, for example, in this point here, okay? Green. For example, what is the displacement here? This is the V capital I, okay? Because this is node I, J, and K. And this is our X, Y. Okay? So if we know this function, okay, and this function is U dependent on xy, and this function here is a V dependent on xy. If we know this, we could obtain that. Well, but Filament method only gives you the displacements on nodes, does not give you displacement on the center, on the middle of the element. Okay, so how can we do this? Well, we know the position of the nodes, okay, and what we know is that this is a plane, isn't it? The surface is a plane. And once you have 3 points, we can say that displacement of any point, okay, of any point should be approximated by this function that I'm going to write. For example, A plus B x y plus C y I, isn't it? Any point inside could be approximate because this is a plane. Well, we can also write this, for example, using mathematics, using algebra. A, B, C. This is the part that we would like to know, A, B, C, because the one x, y, we know it. We know the point that we want to have the reading, but we don't know this. What do we know? We know the displacement of each one of these points. For example, we know this one. This one is the U of xy, xi, yi, which is the same as writing this one. Sorry. which is the same as writing 1xi, the same ABC, the same of here, exactly the same. So this is a polynomial vector. I can change this, saying, okay, this is a polynomial vector multiplied, transposed, multiplied by non-constant variable vector ABC. This is this. This is this. Okay. So if I write this expression to each one of the nodes inside, I will have something like this. For J, isn't it? Just changing here for J. And if I repeat it for K, I will have this. Okay, okay, okay. Well, what I'm seeing here now is that I have a system. If you look at here, the xy, 1xi, yi, 1xj, yj, 1xk, yk are being multiplied by this vector. This is the same as organizing this in one matrix, 1xi, yi, 1xj, yj, 1xk, yk. Okay, and multiply this by this, only these three.
ABC. Yeah.
It will give you the same. It will give you the yi, the ui, uj, uk.
Okay.
So this is similar. Okay, we call this one the moment matrix. Okay, and we use it generally the letter C for it. Okay, so if you look at here, you see that C multiplied by vector A, because this is the same vector, is equal to, let's call this vector DE. Why? Because it's the displacements of the element. But they are only U. So let's use another letter. Let's put it D, U, E, to know that it's only for U's. If I produce the same result but for V, notice that V will be here, V, 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 and we have another set of ABCs to use, isn't it? So, but the X and Y, it will be the same. So if you do the same for the V, it would be something like this. It will be another vector, vector B, okay? For example, B would be B, C, D, E, F, okay? And this would be for V's. V1, Vj, Vk, isn't it? So, but there is a constant here. The constant is the C matrix, the moment matrix. This part is equal in both. Okay, so if I want, for example, to obtain the A parameter, I just jump the C to the other side and put it -1 and multiply to these parts. Don't forget that we already obtained this in a previous finite method analysis. Okay. Don't forget that we already know these values of U, I, J, K are known. Okay, let's do this exercise. They are known. Okay, so we can obtain this, but we know also that our displacement of general points inside of our element. Sorry, I click on the wrong side. Of a general point is given by this. So let's substitute this A, okay, by this value. So I get that our U of general points inside is equal to the polynomial multiplied by A. A is this. Let's write it. It will be something like this. It will be this matrix, exponential -1. It will be the polynomial. Polynomial is this one. Multiply by this part, and this part is this vector. This is the general formulation of the finite method. Okay, this interpolation is the general interpolation of finite method. Why? Because this part here is called the shape function. Let's see what is a shape function. Okay, so if the exponential minus, if I invert this matrix, okay, I will get something like this. If I invert it, if I put this matrix here and I invert it, okay, I will have a matrix, a new matrix, okay, which will have all, let's call it G. All the variables will have maybe a non-zero value, okay, unpredicted, because it depends on the position of the nodes. And I'm calling them by their names. G, well, this could be, for example, 3.1, this could be minus 1.0, this could be 0. It can be any value, okay? This inverted part of this. So these are real values here inside, okay? So let it be like this. So if I multiply, see, if I multiply this matrix for this, that I'm saying that is shape function for this part here, I will get this. I will just copy paste this part so you understand what I'm talking about. I'm copy pasting this part here. Don't worry to just try to understand, okay, the process. Don't worry in trying to take notes because I'm getting too fast, isn't it? I'm writing too fast, isn't it? Okay, and we'll have this anyway, so never mind. But you are understanding the process, yeah?
Yes.
Okay, that's the most important part. This is what we are going to call our shape function vector. And this shape function vector is for this node. Okay? So if I make this operation, I will get this by exponential minus 1 is this part, isn't it? Sorry. Is this part. It's here. You understand? The exponential minus 1 is this, isn't it? So it's this part that I get, okay? Because it is exponential minus 1, see? The exponential minus 1 is this parameters here. So you'll get something like this. This multiplied by that, it comes G11 plus G21 X, Y plus G31 Y, I. First term, next one. This by that, it gets G12 plus G22, G23, and then I don't have the space, I'm going to jump to the next line, here, okay. See, it's going to give you a vector, this is at 1 per 3 blocks, and then G13 plus G23 plus G33 Y. This is the shape function of first node I. This is the function, the shape function on node J. And this is the shape function of node K. Okay. If I plot this function here, just for fun, you'll see something like this. Your initial triangle, the axis, X, Y, and now it comes here and I. And I'm going to copy paste this one 2 times. So I can draw all of them, the J and the K. Let's see what happens. In this function here, I know, and you can plot it, you can do this also at home when you have time, if you have time. If you plot it, you'll see that in node I, J, and K, I forgot this part, I, J, and K, I, J, and K. You'll see that here, you'll get the value of 1. And then all the others get to 0, like this. And you have a function that is something like this. And here is 0. If you plot this one, you'll see that on node J, because it's of J, you get the value of 1, and to the others, it drops to 0. And here, you see that you get the value of 1, etc., and the others get to 0. Like this. Okay, they are linear functions. Okay, so any point inside here will get this one will have this value, this one will have this value. Is this the same? It's xy for everyone. If you make the sum of these values, you make the sum I equal to 1 till n of the values of these, of each one of these terms, it will get you the value of 1 again. This is the unity property of shape functions of finite element method. Okay, this is unity property. Okay, well, if you do this, okay, you know that your interpolation, see that your interpolation, in fact, is what? The value of u of x, y, yi is actually your ni xi, nj xi, nk xi multiplied by ui, uj, uk. So it is this value on red, which is this one, multiplied by this, plus this value here on red, which is this one, multiplied by this one, and this one is this value on red multiplied by that one. And in the end, you have an interpolation. It's the same thing as writing the sum of e equal to n of all of these, isn't it? Multiplied by your u, each one of these u's. Let's put here another letter, for example, L, to not confuse with the L, with the E. You understand this? And this is the interpolation of FEM. Every finite element method uses this interpolation that you are seeing here. Okay, this is a sum, but generally we choose to write it with vectors. Okay, we only write this for our u, but if you do the same, you'll see that for v it will be exactly the same expression. And whatever variable that you have, for example, you are analyzing UV and also in each node you have temperatures. Well, that's not change. You can put VV and okay, in each node you have temperature. So it is the same, but change it for the temperature here. It becomes here temperatures and you have to read the temperature on each node. Notice that this N here does not depend, this N, it only depends on the position of the node that you are reading and the position of the other nodes. See that this G was obtained based on the coordinates of each node. So it is the same regardless the degree of freedom that you are analyzing. So it does not depend on degree of freedom. See now that you can mix and you can combine, for example, these two in one expression. For example, you would be able to obtain, for example, a vector, which is our u, you see this vector here, u x I y I, which is equal to this one. If you make the same, the following calculus, ni, which is this one, 0, 0, the same. I just putting this dashed line so you can see it appearing. Nj, which is this one. These are scalar values, okay? Nj, nk, multiplied by u of node I, v of node I, u of node j, v of node j, u of node k, v of node k. If you make this, you'll see that this multiplied by that will only affect the u's first. And this multiplied by this will only affect the v's. So you'll get the u and the v. It is the same of writing these two separated. Finite element method likes everything combined, does not like separated values, variables. It likes combined variables, okay? This is interpolation. So you understand this, you understand finite element method, okay? This is interpolation. Now you can apply it to everything that you want, okay? to temperatures, to velocities, to displacements, to stresses, everything. So this is the interpolation, okay? So the values that you know are on nodes. This is the values that you know. The values inside the element are interpolated. Okay, they are not known. These are known nodes. Okay, known, interpolated. Okay, well, I don't know if you remember, but for solid mechanics, you are going to read it anyway. Okay, but for solid mechanics, I don't know if you remember the deformation, the strain. Remember the strain tensor? No. The stress tensor. Remember the stress tensor. X. You're going to read it anyway in these days. Okay. Remember this. No. You remember this? No.
Yeah.
No. Okay, never mind. Let's see it first.
Yeah.
So interpolation. You. I'm going to say this because everything that we talk right now, you understand, yeah?
Yes.
Okay. Let's see now the stress. Stress and strain. Okay. Because it is important to understand stress and strain, or else you will not understand filament methods. Okay. For what we are using it with this solid mechanics. When you have a body, okay, any kind of body, you have here, for example, the X, Y, and Z. This body is submitted to several loads, isn't it? F1, 2, 3, 4, 5, 6, and 7. Okay, so we agree on that. Several loads. And if we impose that the sum of all loads are equal to 0, and the sum of all force moments in relation to a point O are equal to 0, the body is static. So it does not move on space. It does not rotate. It does not translate. So it's static. Well, if we chopped our body in half, for example, you come here, okay, with a knife, we do something like this. To drop it here, we chop it using a plane. Okay, for example, like this thickness. Yeah, this plane over here, I'm going to chop our body. Okay, using this plane. Oh. You are seeing the plane chopping the body. It's cutting it. Okay, from here. What I'm going to take this part on. Okay, or maybe this part here, this part. So if we chop our body like that, we have two halves, this part here and the other part here. And this one F1 and this two F7, isn't it? And F6 is missed. Okay.
Yeah.
Something like this. But now, if you see it by the image, you can understand that if you make the sum of forces here, it will be not different. It will be different from 0, and the sum of moments will be also different from 0. So this part will be projected in space with the velocity and rotating, and this part also in the opposite direction. So why, when they are combined, that's not happened? Because here, this is full of inner forces, small inner forces. And these forces, these small, which are equal and opposite to each other, if they are inserted in this equation, now it becomes again, see, this is the capital F, this is the small f, it becomes again 0, and here the same. So it is the small forces that are gluing both bodies. Let's see now what is happening near to this point P. Okay, And near that point P, this is the surface that has been cut. This is point P. This point P is represented by a small area. Okay, and near this point P, we have several, just on that area, okay, several small forces. Okay, and if we make the sum of all those forces, maybe we'll get this vector here. Let's call this on this area of the forces, just the small forces only on that area. It's not multiply, just to say that is on this area. Okay, if you sum all these small forces here, okay, on this area, you'll get this delta F. More, if you multiply, if you divide the force by this delta A, you get a pressure, isn't it? If you make this, don't you get a pressure? Forces divided by area is a pressure. This pressure here is equivalent to the concept of stress, which is an inner stress that is happening inside of your body. So let's call it vector T. In Portuguese, it's tension. Okay. If you now decompose this vector T, because you know that this surface, which is cut, is a plane, as a normal. If you project this vector T in this normal, you get two vectors. A normal vector coming from this side, which is called sigma, and a shear vector, which is called tau. So if you sum the sigma with the tau, you get the T again. Okay, this is the shear that cuts the bodies, and this is the normal stress that stretches or compresses the bodies. For example, if you have a body and you apply only forces on both sides like this, your stress is F divided by A, and your shear is 0. There is no shear. And how the body responds, it stretches. Okay? If you get, for example, a body like this, and here you make a force in this direction, and here you make a force in the opposite direction, but they are not aligned, your body will do something like this. It will collapse because of this. It's the other way around, isn't it? Something like this. But you can see it. So, and this is the shear. Okay, and we will rip out like a scissor. The scissor cuts the paper like this. It takes the two sheets and it makes something like this. Okay. Well, so these two stresses, these internal stresses, we have to know them. Okay, we have to calculate them, but we have to calculate two important directions, which are the Cartesian directions, X, Y, and Z. Okay, because this N can be in any direction, this N. Okay, so we want to cut our body, actually, we want to cut our body in very specific directions. For example, a direction that is normal and parallel to the X axis, this direction, X. So we want this particular N, which is I. You know that I is this vector, yeah? J is this vector. and K is this vector. Okay, you know this. So if you shop it like this, in this point P, the T is somewhere there, and if you project it there, okay, in the axis that you have access to, which are X, Y, and Z, Y and Z, if you project that T over there, you get, for example, this projection that we are seeing here. This will be our shear in that direction. This will be a shear in that direction, and this will be a normal vector. So this will be our sigma x, this will be our tau x, y, and this will be tau x, z. So the first letter represents the direction where the plane was sectioned, that represents the normal vector, and, oh, sorry, this is a z. And the other letter represents the axis where it's being read. Okay, I also make a mistake here. This is y. You understand this? So from this t is equal to this vector plus this vector plus this vector. See that all of them start with the x. On the x direction, y and z. If it is normal, he has the letter sigma. If it is a shear, he has the letter tau, and the other two letters in the index are different. Understand? If you take this example here and you shop it in the other directions, okay. For example, if you shop it, you section here, you have now here the y, here the x, and here the z. So this will be our direction j, which means that our vector now, it can be like to this side, it does not have to be the same side, p. Now we can project it like this. And this will be our sigma yy, because it's the normal. This will be our tau yx, and this will be our tau yz. And we'll have another t, which is this one, which is equal to this. Well, you get the idea, M2. So if you make for the z, actually, if you make the same thing for the z, you'll have another t, which is this. Isn't it? So you can count it. You can count 9 distinct variables. 1, 2, 3, 1, 2, 3, 1, 2, 3, 9. Okay. You can organize their magnitude because you know that, for example, sigma xx vector is equal to the magnitude multiplied by I. So all of them have a magnitude. For example, here, tau xy is equal to tau xy magnitude multiplied by j, and tau xz is tau xz. This is a vector, this is a magnitude multiplied by k. If you select only the scalar values, you can organize them in your stress tensor. And stress tensor is organized like this. It is symmetric, so these two variables are equal, so our sigma, don't forget that our sigma xy is equal to yx, our sigma yz is equal to zy, and our sigma zx is equal to xz. Okay, so you can just represent one of them, you only have 6. Tau xy, tau yz, tau yz. This is your stress tensor. This is only valid for point P. So in our problem, you have here a point P, which is this stress tensor. You have here a point K, which has another stress tensor. A point R, another one. Each point of your problem has a different stress tensor. Okay, so this is why in finite method you get those color maps. Okay, different colors, because each center of the element has a different stress tensor. So of course, stresses give different along the whole domain, okay? You can relate this with the strain. Do you have any questions about stress?
No, I don't.
You know this, don't you?
Yeah, like just like I didn't know, like because of like the language, like when you like try to explain it, I knew
you understand, isn't it? Because I know that you had this in your syllabus of material resistance or something like that. So I know that you already had this. This is another way of showing it, okay? Just that, okay? For example, strains. Strain. Strain is very similar to stress. Stress is an abstract entity. Stress is an abstract entity. You cannot see the stress. You cannot measure directly the stress. You can only measure directly the strain. If you go to the laboratory and you have something like this, okay, and you pull a force here, okay, and you put here an I call it in English. It's an elongation meter that allows you to obtain the force displacement on a graph in the laboratory. And this device here, it reads the extension. What is the extension? The extension is, for example, you have this initial size, you put a force on it, and you get a stress. And the stress was this one, for example. Well, the elongation, the strain in that direction is equal to our U divided by L0. Okay, so if you are looking at the X direction, of course, it's like this, it goes like this. The Y direction is the V that is elongated like this, and our Z direction is the other one. Well, I'm going to put it formally so you understand better. For example, imagine that you have an infinite small cube, okay, which dimensions are dx, this is dx, dy, and dz, x, y, and z. And you apply a force in direction x. Direction x is this one. Direction x is this one. You apply a force. So what happens? When you apply in the x direction a force, it stretches in this direction, correct? So you get a du. This is the initial size, and this is the final size. So your elongation on that direction is your extension, your strain is the elongation divided by initial size. You do it in the other directions, for example, in the y direction. This is initial size. You stretch it, you put it to force, and it gets this size. So it grows a dV. So your epsilon II is equal to dV dy. And finally, if you have here the dz and you put it a force on the z direction, it will grow, it will increase size on this, and the size will be W. W is for the z direction. So you'll get this. These are the three strains, okay, that you get directly from stretching a cube, infinitesimal small cube. It's like in the big problem, okay? But now analyzing a small cube. Well, these linear strains are related with these values here, okay? You're going to see. But now you have here some shear components. It's the same for the stress. You can, for example, get to a cube and apply here a force, okay? And the cube will have a distortion. You can imagine that distortion, yes? Yeah. So let's see on 2D. Apply the force. Here comes the distortion. This becomes, you see here, it will become, for example, our U, and this is our dy. Okay, and this will have here a gamma, a distortion angle. Okay, we are very interested in this distortion angle. Okay, so let's complicate the drawing and let's force our Q to distort simultaneously in 2 directions, like this. Okay, here you have a U, and here you have a V. But this size is the dx, this size is the dy. And here you have gamma under 2, and here also. It is the sum of these 2 gammas that give you the full gamma, the full distortion. If you see here, this gamma under 2 that we are seeing here, I'm going to put it here, I'm going to call it another thing besides gamma. Let's call it here, let's call it beta. And here, let's call it alpha. Okay, so beta is the arctangent of U under dy. Well, it's not U, it's du, isn't it? And dv. Du, dy. Okay, and alpha is the arctangent of dv dx, isn't it? But we know that for small angles, for very, very small angles, the sine of alpha is actually alpha, and the cosine is actually 1. So the tangent of alpha is actually alpha itself, because tangent is sine under cosine. Okay, so the arctangent of this is actually the beta itself, isn't it? So beta is actually equal to du dv, and alpha is actually dv dx, which means that gamma, which is the sum of both, is the distortion on this plane xy, is equal to du dv plus, sorry, it's not
dy.
This is y, isn't it?
Yeah.
Sorry. And dv dx. If you make the same draw for the other directions, you will get that this one is dv dz plus dwv dy, and dxy is equal to du dx dz dwv dx. So you have your strain tensor, which only has the particularity that I'm going to show you. The shear terms have an half here. Okay, this is only the only difference. But is very, very similar to the shear, isn't it? And most important is this one. I know now that this is equal to this, and I can correlate now the displacement field with the strain field. That is the most important part. Okay, notice that in the future, this U here will be our U of the free filament method, and our V is going to be the same of filament method. Okay, and we are going to derive the expressions to obtain our E and our V. Okay.
Mhm.
Okay. Hooke law. Which is elasticity. Well, you know that in 1D, you can stretch a bar with a force here, isn't it? And it will get bigger. So you have here displacements. If you draw your displacement versus the force, you get something like this. We are only interested in the elastic part. Okay. If you divided your force by that area that is here, and if you divide this u by the initial length, you get the strain versus the stress. And the graph will be very, very similar. It's equal actually, but with different unities. The relation between, in this part here, between the strain and the stress is given by the Young modulus. You know that, yeah? Or
Yes.
the elastic, or the elasticity modulus, yeah?
Yeah.
Well, more. This is the Hooke law for 1D. If you have a body, I'm going to do only 2D is easier. If you have a body and you stretch that body with a force, and here is fixed, it will have here an elongation, a strain, and here another one. Yeah. So this one will compress the body. Let's call it V. It's the Y direction, so let's call it V. And this will stretch the body on direction X. So it will be the U, correct? I know that this dimension is a known L and this dimension is a known D. So I can say that my epsilon YY is V under D and my XX is U under L. Okay, up to here is okay. So I know that is another entity, which is the Poisson coefficient. This is letter similar to a V, but is a Greek one, which is equal to minus the transversal strain under the longitudinal strain, which is in this case, longitudinal is where the force is being applied, is the XX, and the transversal is the other direction, is I. And this sign is minus is because of this V. This V is negative because it's a contraction. So this will be negative also in this case. So this will be minus, this is positive, this is an elongation. So it becomes a positive value. The Poisson coefficient is a value between 0 and 0.5, okay? A 0.5 material is an incompressive material like water, for example, okay? So generally, we don't use 0.5. You use it, for example, for soft materials, 0.999, but never 0.5, because 0.5 is an incompressive material, okay? For example, bones have a Poisson coefficient between 0.2 and 0.3. Structures like the inner ear or the muscles have a Poisson coefficient very, very close to 5, 0.5, which is the Poisson coefficient of water, because they are mainly built of water, okay? Well, if we have all this stuff accounted in a 3D problem, the relation is not as simple as this. We can put our stress tensor in Voigt notation. Voigt notation is what is called this, okay? Putting the stress tensor in a vector, a 6-dimension vector, and we can multiply it by this matrix. This is Poisson coefficient, this is the Angulus modulus. And this is the equivalent of the 1D This is the shear modulus. Okay, I'm going to explain what is the shear modulus right away. And if you invert this matrix, because programming this is much easier, if you invert this matrix, which is called the compliance matrix, compliance matrix, this one, without the -1, with -1 becomes the constitutive matrix. If you multiply this constitutive matrix to the strain, you get the stress. And this is like this. Here does not have the 1/2, okay? It's like this. If you multiply this by that, you have the stresses, okay? Mm-hmm. Well, so you can reduce this, the writing of it. Sigma with the arrow inside, which is this vector, is equal to the matrix D, which is the constitutive matrix, multiplied by this one. Or epsilon is equal to matrix S, which is the compliance matrix, which is this one without the sign -1 exponential, okay, not inverted, 1 multiplied by that, okay? So D is equal to S, exponential -1. S is this one. Well, what is this G? This G is easy. When you analyze like this, your cube, you'll get this graph, okay? This is the force, this is the displacement, okay? If you divide the displacement by this side here, okay, you get the gamma. If you divide it by the area, you get the tau. And so here in this part, you can relate the tau with gamma with G. G is the distortion modulus. It's like the elasticity modulus, but for shear, okay? And you don't have to define it. You don't have to go to the lab, because if the material is isotropic, okay, and well behaved, you can define G with the Young's modulus and the Poisson coefficients like this, okay? You don't have to go to the lab to see what is made of, okay? How it's done. Well, I think that with this you have more than enough to start the reading the book, okay?